All right, this is called transformations, vertical translation. Now, it should be called transformations part 1 of 4. That's why we get away with a very easy lesson today. There's other parts coming. Now, I don't want to scare you and be like, oh, there's a tough one coming. Not really. Each section, as it goes along, will be not bad. Tying it all together when it's done, well, okay, that might be a small challenge. But many students find this the easiest part of the course, this transformation stuff, because they really get it. They really understand it. So with that, if you do find this straightforward, I encourage you to knock down this homework so that the next one seems easy as well. That's the one thing that can go wrong, is you can let it start to snowball on you. That's the only thing that is a real danger here. Don't worry if you don't know what transformations mean. I'm going to explain that. Don't worry if you don't know what vertical translation means. That's what the lesson's all about. Math lessons are like that sometimes. The title maybe should be the last slide instead of the first slide. So we'll jump right in. At this point, we should be quite familiar with the following functions. PowerPoint's very arrogant about this. It says, oh, you should know these very well. Let's take it more like, very soon, we better be good at these following functions because we're going to use them a lot. Y equals x, y equals x squared, and after yesterday, y equals root x and y equals 1 over x. But if you're out there going, hold on, you said yesterday the priority was the quiz, so that I made the priority the quiz. And I worked hard on that. And I didn't do much of your investigation/assignment. I sort of was putting that off to the weekend. Good. I'll talk more about these today, and it'll be some good hints for your assignment. If you're done the assignment, maybe I'll say something today that you go, huh, maybe I want to adjust my assignment a little bit. So it works for either group of people. More take it like this. Instead of saying we should be quite familiar, we better get quite familiar with these 4 following functions. Okay? So we'll talk about them. I'll use them as the lesson goes along. Today we investigate functions that are similar in form to the following examples. Here's what we're going to look at today. All we're going to do is take y equals x and go, well, if we do y equals x, what does y equals x plus 1 look like? And you saw that in grade 9. So you might be familiar with that. You might be like, oh, I sort of know what happens when you go plus 1. This one is the one you saw in grade 10. Y equals x squared plus 5. We're going to look at y equals x squared and then go, well, what happens if I do y equals x squared plus 5? And you look at that in grade 10. So that might be really familiar to you when you see it. So all I'm going to add today is y equals root x, and I might add or subtract a number, and I'm going to look at y equals 1 over x. And again, I'm going to try and teach it both ways. I'm going to try and talk to people who have essentially finished the assignment and know what these root x and 1 over x sort of looks like. And I'm just adding on to your thinking so you can fix your assignment up and make it beautiful. Or I'll also be talking to people who are like, I didn't really get to that. I was focusing on the quiz. And now you got some hints about what to look for when you go to do the investigation tonight, tomorrow. Works out good. Timing-wise, we're okay here because you got the weekend coming. This is what we're up to today. The whole lesson is, yes, I understand these functions. What happens when I add or subtract something outside the function like that? Okay, that's all. How do these functions compare to the 4 functions shown above? Well, I just said that. In general, we are going to explore the graphs. Oh, am I able to record things in the way? I'll just move that up here. In general, today we are exploring graphs of y equals f at x plus k, maybe minus. You know, we're just going to see what happens when we add or subtract. And what happens is very nice. You're going to like what happens. You're going to, oh, I'll remember that. That's pretty straightforward. Is it good? Do you need more time? I tried to give you most of it. You don't have to write too much, right? You just got to fill in a few things. It's a more thinking lesson. I don't want it to be all about copying down pages of stuff here. Yeah, that's why I gave you the notes. More time? Is it good? All right. Oh, I'm on the wrong thing. Gotta go there. Let's start by going back to grade 10. And we'll talk about y equals x squared and y equals x squared plus 3. What those two things do. And maybe you already know, in which case, aren't you happy because you already know what's about to happen here. But to do it, and I say this to functions people in grade 11 and to advanced functions people in grade 12 and to calculus people, if you're not sure about a function, let's say you got to the test and you freeze and you're like, y equals x squared, I actually forget, I don't even know what it looks like. Settle down, make a table of values to remind yourself what it looks like. That's what you do on a test. At home, If you have a brain cramp, you'd use Desmos. You'd go to a website and go, just let me remind myself what this thing looks like, and you'd type it in so you could look at it, all right? So you got two methods there. So y equals x squared, let me just go through this table of values just in case you don't know how to square numbers. Yeah? Negative 3 squared becomes positive 9 because it's negative 3 times negative 3, and a negative times a negative is positive. Negative 2 squared becomes positive 4. Negative 1 squared becomes 1. 0 squared is 0. We might have got a little scared of 0 recently, where we're like, oh no, here's the 0. No, squaring zeros, no problem. As long as we're not dividing by 0, we don't have no issues there. 1 squared is 1, 2 squared is 4, 3 squared is 9. Do you remember this thing? What does it look like? What's the basic shape here of y equals x squared when you graph it? It's a parabola. Very important to both physics people and business people. They will talk about parabolas all the time. Not the basic parabola we're looking at. We're going to have to get better at them before we can actually use them in the real world. But very, very important. So here's the table of values for y equals x squared plus 3. And the whole lesson is right here in a couple of seconds. All I do to make the table of values of x squared plus 3 is I take the values I had for y equals x squared and I add 3. I'm literally taking x squared and adding 3. And if I add 3 to each of those, 9 plus 3 is 12, 4 plus 3 is 7, 1 plus 3 is 4, 0 plus 3 is 3, 1 plus 3 is 4, 4 plus 3 is 7, 9 plus 3 is 12. I hope you're bored, actually. I don't normally hope for that. Normally, I hope I teach well enough that you're not completely bored out there. This time, I hope you're bored. You're like, so I just take the y values and literally add 3 to them? That's what we're doing today? Yes, and it's called a vertical translation, and we'll see why when I actually go to graph these two curves. Did I give you those table values? You've already got the table values, okay? You just had to fill in the y's. Okay, good. All right. How do you think the graphs of these two functions will compare? Before I actually show them, can anyone look at those and go, I see what's going to happen here. If y equals x squared looks like this, and y equals x squared plus 3 looks like this, if I graph them together, how are they going to look? Yeah, this coordinate of 0 will be moved up 3. So the normal parabola, here I'm going to try and do it and get a little exercise in the meantime. Those of you on the video, I'll describe what I'm doing. If I just stand here with my arms in the air, like a parabola, to do y equals x squared plus 3, I'm just going up 3. And now I'm on my tiptoes. I've just moved the whole thing up 3. That's the whole lesson right there. That's the visualization of everything that's got to happen here. So let's see them. Ladies and gentlemen, the graphs. There's y equals x squared. Did I give you that? Yes? Now you got to draw y equals x squared plus 3 and hopefully learn everything there is to know about today's lesson. Here comes y equals x squared plus 3. It's the same thing. It's the same thing. The red graph on there is the same as y equals x squared. It's just every point's moved up 3. Now it's a small optical illusion though. It looks like they're getting closer and closer together on the outsides. They're not vertically. If you look vertically, see? 0 moved up to 3. Let me get my pen out and show that. You don't have to write what I'm going to write on here, okay? I just want to show, I'm just going to do some good teaching here, hopefully, for both you and people who are watching this on the video. Oh, no, red? No, blue. Let's get a color blue that looks a little different. Ink color blue. See? This point at 0, 0 got moved up 3. This point at 1, 1 got moved up 3. This point at 2, 4 got moved up 3. Everything's moving up 3, but the shape of the parabola makes it look like it's getting closer and closer together because it starts taking off so fast. So don't let the optical illusion fool you. Everything just got moved up 3. That's all that happened. To which you go, okay, so listen, looking forward to a quiz or a test on this. If I was doing y equals x squared plus 3, what would I do? Either way, either strategy works. You could build a table of values for y equals x squared and add 3 to everything and then just graph this. That works. The other method is I'm going to go ahead and graph y equals x squared And then I'm going to take each point and move it up 3. Both of those methods are perfectly valid. So you got 2 ways to handle this situation. Is there some questions that come up here? So what happened? I already over-explained it. The graph of y equals x squared was shifted up 3 units. Why does this result make sense? I hope I've explained that too. We have just added 3 to the y values of the function y equals x squared. Now, if you think that's really easy, let me just fast forward Friday, Monday. By Monday, we'll have a few easy things we'll be juggling. That's the only way this gets hard, is because we'll be juggling multiple easy things at once. Okay? So that's the future of this. Each lesson by itself is like, oh, that's pretty straightforward. But then when you start combining them, things get a little tricky. Not nearly as hard as the previous 2 chapters. No. But we're going to get a little tricky here coming up. This transformation, here, now we finally understand the title of the lesson. This transformation is called a vertical translation up of 3 units upward. Why is it called vertical? Do we know this word? I don't know, maybe not. You might have got this far and you really didn't need the word vertical. Does anyone know a reference? Where have you heard the word vertical before? Did you use it in grade 10? Great. Vertical transformation, up 3. Great. In real life, though, outside of the math class, when does the word vertical come up? Jumping. You're doing a vertical leap, which means you're going upwards, not a horizontal leap, which is this way, which we can do too, like the long jump, but vertical leap means upwards. Probably in basketball they talk about that. Oh, what's this vertical leap? Maybe at the combine in the NFL. I don't know if they care if they can vertical leap or not, probably not. But vertical, upwards. There. Did I yammer on long enough to let you copy down what you had to copy it? There? Was it enough time? Yeah. They say yes. Was it enough time for everybody? Do you need more time? Is it good? Thumbs up? It's good? Yeah. Am I going to make it time-wise? I don't know. I don't even know what slide I'm on. This slide is not working. What's happening? Let's do it with the function you learned about yesterday. But I got to remember, I'm teaching 2 groups at once. One group who's like, yeah, I sort of saw what root x looks like, and another group which didn't really finish that and doesn't know what root x looks like. So, if you get to the test in this chapter, and all of a sudden you have a brain cramp and go, I forget which one was root x again. You just go to a table of values. And I'm going to build a whoops table of values over here. What I'll call, by whoops, what I mean is, it could be when you go to build a table of values, because you don't know what you're doing, you build a table of values that doesn't work very well. I still think the table of values is really good. But I was having a discussion with some people yesterday about table of values, and we talked about, is negative 3 to 3 the best x values to use? And I hesitated. They saw me hesitate. Because the answer to the question is, I'm not sure if negative 3 to 3 will give you what you want in a table of values. But it will tell you which ones you should use. So it's a good one to start with. So the answer that I will like best is yes. Go ahead and start with negative 3 to 3 in your table of values. It might not be the best choice. But once you do those ones, you'll be in better shape to make a good choice. For instance, if I did this, square root negative 3, if you put in your calculator, you get undefined, or you get some kind of error. You can't do square root of negative 3, not with any numbers we know of. And you can't do square root of negative 2. You can't find a number that multiplies by itself and gives negative 2. Again, in our numbers. So do you see how these values were a bad choice, but they're still a good choice to start with, to go, oh yeah, I remember the square root function now. Remember, this is you on the test going, oh yeah, don't use negatives. Then it starts to work. Square root of 0, 0. You're happy. Square root of 1, 1. You're happy. Things are going well. Square root of 2, 1.4. Perfectly legitimate. There's no problem with 1.4. It's just hard to graph. We could have used 2 yesterday. You just wanted to go, oh, about 1.4. Works fine. 3, square root of 3, you get about 1.7. Hard to graph. And then you get to 4, and you go, root 4 equals 2, and you go, oh, 4 is a good choice. That gives me a nice point. And now you see why I gave you the table of values I did yesterday. Because I said, why don't you try these ones? Yeah, let's not waste your time. The first time you're seeing this, why don't you try the ones that will square root? They're not the only allowed values. They're just the ones that square root nicely, so you could make your graph very easily. So then that was the table of values for y equals root x. Now, from there, then we can build a table of values for root x minus 5. And all we do is take the values from root x and subtract 5. 0 minus 5 is negative 5. 1 minus 5 is negative 4. And you just go minus 5 all the way down. That part of today's lesson, I don't think that's particularly hard. You're subtracting 5 from all of those. So then, how do you think the graph of the two functions will compare? What will root x minus 5 look like compared to root x? And that's okay, even if you don't know what root x looks like, because you didn't do the investigation yet. How will these compare if I'm going to subtract 5 from all the y values? Just down 5. All of that just to say, if you're subtracting 5 from the y values, you're going down 5. Okay? Now, here's a hint on the root x function now. For those of you who haven't got that far, there's what the root x is looking like. It looks like it is a sideways parabola, but only half of it. You only get half of the parabola. That's a perfect description of root x. Half a sideways parabola. Good. So if you haven't done the investigation yet, that's what you should expect to get. If you have done it, you're like going, oh, good. That's what I got. That's good. I'm happy. Then root x plus 5 is that whole thing, or root x minus 5 is that whole thing moved down 5. No optical illusion this time. It really looks like it moved down 5, I think, this time. So that one is a very good example for showing what's happening. Move my recording thing there, just out of the way. There's root x minus 5. You should put it on, and you should label it. It could be your grade 9 or 10 teacher told you to label every graph on there. Was I there for grade 9 and 10? If I was your grade 9 and 10 teacher, I probably wouldn't have said too much about labeling. Till now. If there's 2 of them on there, now you got to label it. When there was only 1, labeling it seemed like, well, why am I labeling this? But they were getting you ready for this moment where there might be 2 graphs on there, and so now we better label them. So what happened? We already predicted it. The graph of root x was shifted down 5 units. Why does this make sense? We subtracted 5 from all the y values. And this transformation is called a vertical translation of 5 units downward. We'll use those words again and again this chapter to describe this situation. Vertical because it's up, down. But I think I've given you a load of copying there, have I? So I have to wait? Is it a lot? Medium. Medium, we say. I'm going to peek to make sure I'm okay time-wise here. How am I doing? We just did that one?
We just did that one. So to do these.
2, 5 more slides. Okay, 5 more slides. Okay. We're going to be okay time-wise. I'm very happy. You should be happy. You're like, what could this homework possibly be? Seems like it'd be pretty straightforward. Maybe I can work on my investigation tonight and make sure I'm going to get a great mark on that too. I'll mark your quizzes tonight too. Yeah? It's beef stew night at the Todd House. We'll be getting in our pajamas right when we get home from school, eating beef stew, relaxing. So I'll have time to mark your stuff. Do you need more time there? Did I yammer on long enough? More time? Yes? Okay. I didn't look at my watch to rush you, by the way. I looked at my watch because it buzzed. So I was like, what? What's happening? Is there something going on with sweaters today? Are we allowed sweaters today, or is it just starting to spread? It's really cold. It's too bad they didn't make St. John sweaters, eh? They're surprisingly not very warm. Yeah, we talked about that. Wouldn't a hoodie be nice? Wouldn't a nice St. John's hoodie be good?
Even just like a nice cream. Like this is the best, but it's got holes in it.
Can you layer it and get away with it? Like, can you put something under the St. John's sweater and put the sweater over top and sort of? Not really. It's a problem. They'll figure out that I'm not yelling at you about this, and then they'll start appearing. So we're going to have to think about it. Did I buy you enough time? Are we okay now? Good? All right. An example. Okay, what's this literally going to look like in the homework? This is what it's going to look like in the homework. It says sketch the graph of root x plus 2. But can we jump ahead here? Can someone leap ahead and go, I know what this is going to look like. What does root x look like? Even if you haven't done the investigation. Yeah, someone's drawing in the air this half a sideways parabola. But then if it's moved up 2, what's going to happen? Same thing, just up 2. Okay? So again, this should be easy, but remember, as the days go by here, the next 3 or 4 days, we're going to have to juggle 3 or 4 easy things at once. That's what's going to be the challenge here. So this will be pretty straightforward. Plot some key points for the base function of y equals root x. Perfect squares are a good choice here. Yeah, use things that can square root. Why not? So here they are. 0, 0. This is the points most people use to graph this thing. 0, 0, 1, 1, 4, and 9. Why? Someone in their own words. Don't use my words. 0, 1, 4, 9. Why did I choose those ones? They make perfect squares. And so if I square root, I'll get nice numbers. Could I do 2, 1.4? Yeah, it's on the graph. But geez, that's awkward, right? We like points that are right on the graph. Lightly sketch y equals root x. Actually, that's going to be important for you. If it's not the graph that you want, but you're using it, just draw it lightly so it doesn't interfere with everything else you're doing. Then, dark, or in another color. Some people like using another color here. This is where some nice colored pencils come in handy. You go, in another color, go, okay, now take all those points, and what do we decide plus 2 does? Up 2, okay? And the reason I'm hesitating there is because soon we're going to have to be able to juggle, so we got to be able to look at it and go, which one does this do? Yeah, so anyways. So you take all those points and move them 2 upwards, and there's what you get. Ooh, I don't like that PowerPoint didn't show the points. Okay, I'm going to put the points on for you. Pointer options, ink color, red. So I take this point and I move it up 2. I'm going to really darken that in. I take this one and move it up 2. I take this one and move it up 2. And I take this one and I move it up 2. And that's enough to get the whole picture. Now, technically speaking, this should have an arrow at the end saying, and it keeps going. That's the investigation says, oh, take it out to 30. And all I was trying to get to, and I don't think it phrased very well. I think it confused people. All I was trying to say is, you really should draw an arrow to say, and this keeps going. I can do square root of 15. I can do square root of 20. I can do square root of 90. This graph will continue like this. But I've established, it's not called a pattern anymore. I've established the trend. This is what it's going to look like. Okay? Do you have questions there? Do you need more time? Label it. Oh yeah, don't forget to label it. There's y equals root x plus 2. Put that label on there of your final graph. That way if things get a little messed up, I know which one you're referring to, which one you think is root x plus 2. And again, some people like switching to another color here. They bring a red pencil crayon to go, there's the final one. So there's no doubt about which one it is. More time to label it? You're good? Did you label it anyways? Did you already have it labeled before I said label? Good. Good stuff. Maybe your grade 10 teacher was all over that. And then we could ask questions like, what's the domain and range? Okay, now, first little difficulty here. The homework questions should say, could say, something like, instead of saying sketch the graph of root x plus 2, maybe it'll say find the domain and range of root x plus 2. It won't say sketch the graph. And then someone will text me and say, Mr. Todd, do I have to graph it to find the domain and range? And my answer is, if you're asking me that, yes. It is possible to get so good at functions that you can look at them and know their domain and range. But not when you first meet them. Most of the times you're going to graph them first. And that's why this example graphs it first, then asks about domain and range. Because once you have the graph, then you've got a shot at domain and range. What's happening? Oh, I got to write it in. I got to write it in myself. I thought the PowerPoint had it on there. That's okay. I know how to write. Domain. Domain, 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 domain. Domain. Are there any x values that are restricted here? Are there any x values I cannot use? Nothing below 0, yeah? Root x is restricted. So the way we write that is we had x element reals, which means use all the x values. Use decimals, use fractions, use everything, except don't use things less than 0, so use x greater than or equal to 0. That might have been the only sticky point on the quiz, I think. I hope most of you, the rest of the quiz was pretty good, but writing these up is a little challenging when you're first learning it. So a little more practice here. How about range? I only see some. Ooh, Nathan, look at that one. Yeah, I know. I rushed it. I'll leave it there just so you don't feel nervous about that. Yeah. Y element of reals. What's the restriction here if you're still practicing these? What y values are allowed? Anything above or including 2. So y greater than or equal to 2. And I know that notations, I worked hard on the quiz. I went, don't make their mark on the quiz totally based on this. So there's only 2 questions that force you to do it, giving you, and actually I think one of them, you didn't even need a restriction on one of the variables. So hopefully that made it that your whole quiz mark wasn't based on your ability to write these out like that. Did we really need the graph to state the domain and range? I say yes. The PowerPoint says no. There is a way to make appropriate adjustments to the domain and range of the regular graph. Watch this and see what you think. I'll try to do it using the original domain and range. Okay? So the domain for y equals root x. Okay, I'm going over here, I'm going to go for y equals root x. The domain was x element of reals such that x is greater than or equal to 0. The range was y element of reals such that y is greater than or equal to 0. Do you know what I mean? Like if I go back to y equals root x, there it is right there. Where is it? Oh, you had it on the screen there. There's y equals root x right there. Its domain was x greater than or equal to 0, y greater than or equal to 0. Okay, so I could use that domain and range instead of the graph. And then I could look at the transformations and then go, okay, well, what transformations have gone on here? If I was going to change this now to y equals root x plus 2, if I'm moving it up 2, does that affect the domain or the range? The range. And if that was difficult to answer for you, just graph them. Yeah? But you could technically go, oh, well, if I'm moving up 2, then the domain stays the same. And the range, I've got to move up 2. So y element of reals such that y is greater than or equal to, I've got to move it up 2. So this goes up to 2. Do I suggest that? Only if you completely understood what I just did. Advanced functions, calculus, all those people. We usually graph it first. We just graph it and say, I'll get the domain and range once I graph it. Okay? But if you really get this, that's what the PowerPoint's trying to say, is you could look at the domain and range of the base function, and then you could modify from there. Okay? So it's available to you. Any questions about that? I just moved the range up 2. That's all I did. Yeah. More time there? If you get the graphing, stay there. This isn't me warming up to do something tougher later or anything like that. You don't need this unless it makes perfect sense to you. Try this one. State the domain and range of y equals 1 over x minus 3. Maybe a graph will help. Yeah? But what does y equals 1 over x look like? Oh, what does y equals 1 over x look like? Did you get this far in the assignment? It's got 2 pieces. Let me see if I can do it. Over here, it's like that. And over here, it's like that. It reminds me of, I used to call it the karate curve because I took some karate lessons when I was a kid. And it seems like I'm doing some karate there. drawn this curve. Yeah, little blocks there. But here's the y equals 1 over x graph. There's your hint if you haven't worked on the investigation yet. There's what it should look like. But you get your hint from Desmos too. Yeah? Desmos goes, oh, that's what that looks like. So now, y equals 1 over x minus 3. What's going to happen when I go minus 3? This is what we're supposed to get good at today. Minus 3 will move the whole thing down. Okay? So if I was going to graph this thing move down, the PowerPoint's going to do it for me in a second, but here's what I suggest you do. In a color that's light, or in a pencil that's light, so what color am I going to choose here? A color that you can just barely see. I'm going to go with this light green. You tell me if I've chose a good color that you can barely see. If this whole thing gets moved down 3, then this horizontal asymptote, it's called, this line across here has been moved down 3, and that's where it goes. How did I do? Did I choose the right color where you can just barely see it on there? But the vertical asymptote doesn't get moved because I'm moving down 3. That really helps to go, where did this thing move to? Move those two literally guidelines to help you go, where did this thing move to? And then move those two curves downwards like that. And there's where y equals 1 over x minus 3 moves to. Now I can answer domain and range. Oops. I thought the PowerPoint was going to do it again. Am I still in yellow? Domain. Domain. Pen. Pointer options. Pen. Pointer options in color yellow. Here we go. Here's my domain range. Domain. How good a hint is this for your investigation? Literally tells you one of the answers from the investigation right here. Are there any x values that aren't allowed? There's one. There is exactly one x value not allowed here. You can't put 0 into this thing. It's also the restrictions you already know about. If I put this on the last test, you'd know the restriction, x can't equal 0. So here we go, x can't equal 0. And it happens with the range too. Y element of reals, but there's one y value.
Hello, Mr. Todd.
Hi there.
Is Emma Lawson in class?
No.
Okay, thank you.
What y value is not allowed? Oh, Emma is here. Oh my goodness, Emma. I'm so sorry. I thought he was asking about Emily, but not Emma. But you are here. Maybe you should go see Mr. Lynch and see what he's after. Did you have an appointment or something? Oh, okay. So that's probably what it's about. Sorry, Emma. What y value can't you have here? Totally giving it away here. -3. Because that y value that wasn't allowed for 1 over x got moved down 3. Okay? If that's a little tricky, that one, well, I'd maybe do the investigation first and get used to 1 over x a little more. No questions? More time? Making the leap to generalizations. I hope this is pretty straightforward the way we've presented it. Describe how the graph of the following functions can be obtained from the graph of y equals f of x. This looks weird at first. It says y equals f of x minus 9. You're like, how am I supposed to answer the question if I don't know what f of x is? But the question is asking, what happens? If I take f of x and go minus 9, what's going to happen to the graph? Vertical translation down 9. That's all this question's asking you to do. Yes, we don't know what f of x is. But we do know that if I take f of x, whatever it is, and go subtract 9, that's going to vertically translate it down 9. How about this one? Anyone want to try to use the fancy words and catch the difference in this one? What would this one do? Nathan whispered it. Vertical translation, but this time up 7. Yeah? Only thing I could think of to try to fool you after all this. Y plus 2 equals f of x. Move it over first. It's got to be y equals. Is that a rule? That it's always got to be y equals? No, it's not actually. But the only way it's going to work like we've been doing is to have it y equals. So then that's a vertical translation. Oh!
It's down. It should be
Look at that, I wrote the wrong thing. I got so distracted. Fix that. Silly Mr. Todd. When I moved it over, it should have become minus. It's always a negative, eh? It's always a negative. Down. Down. 2. Woo! Just had a mistake in my video, wouldn't I have been sad? Is it okay? As tough as I can get, I think, in this. That's the toughest thing I could probably do with this stuff. Okay, the last slide is just a conclusion. Just like, let's just get this all framed in our mind, what we're supposed to know when this is over. The graph of y equals f at x plus k is a transformation of y equals f at x. If k is greater than 0, we're shifting upwards. If k is less than 0, like if it's a negative, so let me just put that there just in case this messes you up. If it's a negative, then it's translating k units downward, whatever the k is, 2 or 7 or 9 or whatever it happens to be. Oh. Any questions on the generalization? All right, this stuff gets, I don't say it gets tricky, but there'll be many things to balance here. Make sure you're really good at this so that if things do get a little tricky along the way, you're ready to handle it.